All right, so in this video, I want to talk a little bit about strategies for working with integrals that involve rational functions. Now, there's not only one approach to this, and so we want to consider what are the things that we should try first, what are the easiest things, what are the things that are not going to work in particular circumstances, and essentially develop a kind of sort of big picture so that we're not needlessly working through problems that we're using strategies that are not actually going to work for us, and we just get to a dead end. A certain amount of persistence in math is important, but nonetheless, we don't want to waste any more time than absolutely necessary. Now, among the different strategies that we have for working with rational integrals are algebraic techniques. So things like doing long division, factoring, things like that, completing the square can come up. We may have partial fractions that we want to apply, which is explained in another one of my videos. We may have to do log integration, so making a substitution for the denominator. We may have inverse tangents that we have to worry about. So there's a lot of things that we have to consider, different approaches. We may even be able to do, in some cases, integration by parts, depending on, or trig substitution, depending on what's available to us. So it's a good idea to have at least a short checklist of things that you can consider before you get too far into the weeds. So the very first thing that you want to think about when you're doing an expression involving a rational function is it a proper rational function? Is the numerator a lower degree than the denominator? Because that is what's considered a proper rational function. Some of the techniques, like partial fractions, are not going to work if the fraction is improper. So you're going to check if the numerator has the same or higher degree than the denominator, then you need to do long division before you proceed. That will simplify your problem, and then it may open up other avenues for you to proceed from there. But that is always the very first thing that you want to look for, because, as I said, a lot of these other things are not going to work if that's not the case. Now, once you get your radical or rational expression into a proper form, then you want to consider possible use substitutions. Use substitutions are going to be easier than doing partial fractions or other things like that. So you want to see if that's at all possible. So if it's a log function that you're going to end up with, you want to check the denominator. If I take the derivative of the denominator, do I get a constant multiple of the numerator? If you do, then you can just let u equal the denominator, do your substitution, and you end up with a log of the denominator, give or take a constant. So that's straightforward. The one thing that students will sometimes forget to check, at least in my experience, is if you can do an inverse tangent substitution. You do a substitution to obtain an inverse tangent. So it's fine. It's a good idea to check for the log, but don't forget, if you have a sum of squares in your denominator, or you can rewrite your expression possibly by completing the square as a sum of squares. If you take the derivative of your u function in that expression, the function that's being squared, does that help you get to your numerator? Now, sometimes this will be obvious, and sometimes this will be less obvious, but it's always worth inspecting, always worth thinking about, because again, this is going to be an easier procedure to do than, let's say, trying to factor the denominator that doesn't factor. And then finally, if you have linear factors in your denominator, is it an integer power or is it a power of a linear binomial? If it is, you may be able to just use a power rule on it. So, do you want to check, is this a perfect square? maybe the derivative of my factor in my denominator is in my numerator, or maybe it's just a linear factor that's being raised to some power, and then my numerator is just a constant. I may be able to apply a power rule. So there are 3 ways that you can integrate this, potentially with substitution. And again, you want to check those before you try some more advanced type of technique. Now, it is certainly possible for some of these rational expressions to potentially be amenable to trig substitution. Particularly if you have a lot of squares, that might work. The downside of that is you have lots of terms. You're not necessarily going to make your life a lot easier doing that. If you have one term in the numerator, and you have like a radical, again, like not necessarily even a radical, but just like a sum of squares or something like that, it may be that trig substitution would be effective. But if you've got like a crazy multiplied out polynomial, then that's just probably not going to be the best strategy. So trig substitution, I would suggest is, except in various particular cases, probably a sort of option of last resort. Now, if it's not a log problem, and it's not an inverse tangent function, and it's not going to be amenable to a power rule, then probably you want to start thinking about techniques that are specifically for rational functions, like partial fractions. Now, in order to apply partial fractions, you are going to need to be able to factor the denominator. Now, if your denominator is already factored in factored form, that's probably a good hint that you can jump to this point. If it's not already factored, then you're going to have to try to factor it. Now, if you haven't done factoring in a while, then this may be like, I have no idea how to factor stuff. So some things to think about. If you have a difference of squares, again, there may be other ways around this, but a difference of squares factors very easily, and then you can apply partial fractions to this. If you have a sum or difference of cubes, there are formulas for that. You may need to look them up if you haven't used them in a while, but they do factor, and then you get one linear factor and one quadratic factor, which will not factor further. The linear factor will be relatively straightforward to integrate once you find the constant that you need. The quadratic factor may need a little bit more work. You may need to complete the square or something like that, depending on how complicated the expression is. You may have a problem that was set up specifically so that once you do your partial fractions, the derivative of the denominator is in the numerator. So once you do your partial fractions, after factoring, you want to think back to our previous discussion about how do I integrate this standalone rational function before things like completing the square and things like that. You may also want to think about factoring by grouping, particularly if you have 4 terms in your problem. You may need to collect them 2 by 2 in order to get a common factor to factor out. You want to think about, is this a perfect square? Because perfect squares may lead you to some sort of a power rule that will be easier to work with. If none of those things seem to work, then you can also try graphing the unfactored denominator and seeing if you can find any rational roots. Again, textbook problems will tend to give you nice rational roots for at least one of the factors so that you can factor it out. Whereas like in the real world, just some random polynomial probably won't be that nice to you. But graphical methods for textbook problems, if you can find one rational root, then you can factor that out, again, divide it out, synthetic division, long division. And then from there, you'll have one power less. Hopefully, if it's just a cubic, that'll get you to a quadratic, and then you have more methods to use. Now, again, expect the roots to be rational for textbook problems. The one thing that you want to keep in mind is in particularly in Calc 1 and Calc 2, and before you get much further on in your math education, you're almost never going to encounter problems that involve complex numbers that you're going to have to work with as complex numbers. So if you've got a sum of squares, don't feel like you have to factor it into linear terms because you don't want to work with the complex numbers. That is a whole other class a few years down the road. Certainly it can be done. Complex numbers are just constant. So, but then you have this whole simplification issue that you'll have to worry about later on. So it is just best easier to stick with our techniques that involve only real values. And as I mentioned, if you have quadratic denominators and you end up after partial fractions with both an x and a constant, you may need to split those up into two separate terms in order to do the integration, or they may integrate as they are. That may involve some tricky algebra, so just kind of be on the lookout for that. And as I mentioned earlier, in some cases, trig substitution may apply, but that, as I mentioned before, is kind of a technique of last resort. If all else fails, you can try this. But it does have to have sort of a sum or difference of squares component to it. If it's just like a long string of polynomials, trig substitution won't be much use. Okay, so I wanted to look at a couple of examples and kind of think through, like, what are these kind of examples suggesting an appropriate technique would be. So I have, for instance, to start with, I have 3 examples here that all have x squared plus 4 as our denominator. If I start with the top, the very first thing that I should be thinking is I have x squared over x squared. I should do long division to simplify this before I go any further. Once I do the long division, it's actually going to end up, the remainder term is going to end up looking a lot like this one. In this particular case, this is a log integral. I can set the denominator equal to u, and the derivative will be 2x. That is a constant multiple of what I actually have. And so I can fix the fact that the 2 is not there. But that would be just a u substitution producing a log function. This case, there's no x. So this is not a log function. This is my inverse tangent function. And for this one, this is just 1 over a inverse tangent of x over a. So again, don't overthink. Sometimes we get into this habit, okay, I have all these terrible integration techniques, and so I feel like I need to apply them. Always start when you're approaching a new problem from the most basic techniques and kind of work your way up to the more advanced techniques. Even if the more advanced techniques can get you through the problem, nonetheless, you'll be working a lot harder than is absolutely necessary. So we introduce these in a order for a particular reason. And so try to take advantage of that, procedure. All right, so here's another example. Now, this particular denominator, it is factorable, so that might suggest partial fractions. It is a lower degree in the numerator than the denominator, so it is proper. But still, it's a good idea to check. If I take the denominator to be u, do I get the numerator? And the numerator, if this was a substitution, should be 2x plus 1. And I don't have that plus 1. So what that is going to suggest to me is that this actually is a partial fractions problem. Factor your denominator, set it up, and then proceed from there. Similarly, this one looks very similar to the previous example, except this one does not factor. So what are factors of 6 which add to 1 as compared to factors of 6 that have a difference of 1? This one will factor. This one will not. So in this particular scenario, you should be thinking about completing the square. It's not going to be a pretty constant when you're done with it at the end, but that in the end, that's somewhat doesn't matter. You can work around formulas, but complete the square. And then this will be an inverse tangent integration. Completing the square almost always results in an inverse tangent. That's usually how they're set up. In this case, again, we wanted to check this is a proper fraction, so we know it doesn't need long division. If I take the derivative of the denominator, I do in fact get that 2x plus 1. So there's no need to worry about the fact that this denominator doesn't factor. I have the derivative of the denominator in the numerator. That will produce a log problem, a log solution. Now here's a couple others. So again, is this a proper fraction? This one is. This is a, if I take the derivative of this denominator, do I get the numerator? I do. The derivative of 3x cubed minus 8 is 3x squared. Again, that constant we can fix with u substitution. That is going to result in a log integral. On the other hand, a problem like this, 3x cubed plus 8, I take the derivative, I get an x squared. I do not have an x squared. So that is going to, again, be the sign that I should be trying to apply some other technique. This is not a sum of squares, so this is not an arctangent problem. These are cubes, and that means I should think about factoring and applying partial fractions. Again, if you haven't used the cube, sum and difference of cubes factors for a while, you may need to look up the formula. But this is a cube and this is a cube. And so you'll be able to separate this and solve for your 3 coefficients that you need. And then from that point, then you would have to again reconsider those things that we were just looking at in that previous set of 3. Is this something where I have to complete the square and get an arctangent, or is this a log problem? Now, for these 4th powers in the denominator, again, we want to think about what are our techniques going to be. If we have a higher degree in the numerator than the denominator, as we have in this example, do your long division first and then see what happens. This denominator is factorable, so if it doesn't yield to some of our u substitution techniques, then factoring would be the appropriate thing to do, and then apply partial fractions. In a problem like this one, it is already a proper fraction. If you take the derivative of the denominator, you get 4x cubed. So again, this would be a substitution problem. You could probably do this with trig substitution, but why would you want to? This problem, on the other hand, this one you might want to do with trig substitution. This is a proper fraction. This x to the 4th plus 1 does not factor. It is a sum of squares. And the derivative of the denominator is not x squared. And if I want to use inverse tangent, then my u is actually going to be the square root of this x term. So my u would be x squared. That's the derivative of that is x, well, 2x. I have an x squared, not an x. So this would not yield to inverse tangent with a substitution. This you might need to do trig substitution on, because again, it doesn't factor. If this was x to the 4th minus 1, you could factor it just like we did down here after doing long division. But the fact that this doesn't factor suggests that you might need to resort to trig substitution. That's probably the strategy that I would go with. Is again, it's a kind of an uncommon circumstance, but that might be the way that you have to proceed here. For this one, again, you have a difference of squares in the denominator. The numerator is not the derivative of the denominator. This one I would probably apply partial fractions to. You don't have to do long division first, but because it is factorable and this isn't an obvious U substitution, I would probably do that. On the other hand, in this case, it looks very similar. The denominator does not factor though. And so that's where you have to hope that one of your U substitutions might work. In this case, similar to this example, this denominator is the sum of squares. So if it's an inverse tangent, then my U is going to be x squared, because the function in the denominator is the function squared. So x squared squared is x to the fourth. U is my x squared. I take the derivative, I get 2x. That is a multiple of what's in the numerator. So I can actually do a U substitution on this and then proceed from that point on to get an inverse tangent as my result. So again, when you're dealing with these rational functions, the idea is try to figure out what kind of strategy to use. Think about it, sort of the big picture, before you just sort of plow ahead. There are clues in the problem. Denominators that don't factor will sort of leave out some possibilities, like partial fractions, but they will sort of reduce the possible range of things that you can attempt. If your denominator factors, still you want to see, just because it factors doesn't mean I have to factor it, especially if I can get around a situation where maybe I can just do a U substitution and be done with it, instead of having to do partial fractions and doing a lot of work and then ending up with a much more complicated solution than was really necessary. So again, taking a minute or two to think about your strategy and how you're going to apply that to your problem solving can really save you a lot of time and hassle and aggravation going down roads where, oh, I tried integration by parts and then I got stuck. Because you don't really have to apply integration by parts to any of these examples. That's not to say that that you'll never apply integration by parts, but you would need like just a linear term in the denominator for that to be even conceivable.